Sitting at my kids' piano lesson and it's all quiet, and I'm going to do the lecture that I did the other day, but slowly. This was the problem actually that you had on your in-class assignment. I hope it's much more clear. I think the issue that I saw in class was that you didn't understand that the 2 points, one of them is a variable point. That's really important to understand. I'm going to skip over that since I already have that in class, and I'm going to move to the Webassign problems that we uncovered in class today, but covered very quickly. If a PowerPoint will let me. So I'm going to do 2 Webassign problems on this module. The first is the square root of 5 times an. It's a recursion equation. We already dealt with a recursion equation on the first quiz, but if we want to do this again, excuse me, I'm looking at a problem where an plus 1 is defined by the square root of 5 times an. So I can create a table of points, and the first column would represent x's and the second column y's, and you notice that I have set it up like an xy plot so I can actually plot them. So I'm creating my sample sequence from the recursion. I plug in n equals 2. To get the next an, I plug in n equals 1 in for the n. Not n equals 2, but n equals 1. There's some confusion on this in that I saw in the quiz. You would plug in n equals 1, which would give you square root of 5. That's approximately 2.2360. They wanted the calculation to 4 places. Now I got lazy. I went ahead on Excel and cranked this out. And you can see here I have the first 10 data points, and it looks like from the numbers that it's converting to 5. I can stretch this out much farther than 10 on Excel and see what it's converging to, and I see that indeed it's leveling off at 5. So I would say that it looks like it's converging to 5. Now on Webassign, you're asked to actually select the graph, check which graph it is, and where it converges to. You get all this information right on Excel. So I really recommend that you try to do this, and I will show you how to do this in a second. On the exam, what I'm going to do is have some laptops open in the front and allow you to use Excel on the problems. So familiarizing yourself with Excel at home is probably much more valuable than learning how to do things on the calculator. So in this problem, this was a word problem. This is number 5. You have a doctor that prescribes 100 milligrams of an antibiotic tablet to be taken every 8 hours, and just before each tablet is taken, 20% of the drug present in the preceding time step remains in the body. So how much of the drug is in the body just after the second tablet is taken? Well, I think in a math way. I think you can answer this question without thinking much, but I started thinking right away. I defined a variable, let dn be the amount of drug in the body after the nth tablet is taken. D1, right after I took the first tablet, I have 100 milligrams in my body. The second tablet, well, I have a new 100 milligrams because I just took my second tablet. However, I still have 20% of the first tablet left, which is 100 plus 0.20 times 100, which gives me 120. And you see that Webassign got it right. They have 120 also. How about the third tablet? Well, I would do the same process. I use the same recursion. D3 is 100 plus 0.20 times D2 from the recursion. D2 was 120. We just calculated that. I have the answer still up here. And then I plug this into the recursion, and I get 124, which is the second answer. You don't need equations to get these answers. You can just use common sense. The third one that they have here is the recursion equation. Notice they use Qn for quantity. I use Dn for drug. But you see that the recursion equation I came up with matched their recursion equation. The amount of drug in the body in generation n plus 1 is always 100 because you just took a tablet times 0.20 of whatever was left before, which was Dn. Now the next one, they wanted you to write it as a formula. They want an answer. And here's how you do this. You symbolically start to recurs, if that's a verb, on its own. So D2 was 100 plus 0.2 times 100, but this time I'm not going to actually crank this out, the value out. I'm going to leave it as a variable. Leave it as 100. But notice the 100 in the two spots here that I've highlighted. You can actually do algebra to numbers, factor out the 100 to the left as the distributive law, and you get 100 times 1 plus 0.2, and I'm not going to combine that. D3, I can do the same thing. I get 100 plus 0.2 times D2, and 0.2 times D2, I just took that 100 times the quantity 1 plus 0.2, and I have it written here instead of D2. Now I have 100 here, and I have 100 here, so I can factor it to the left. So I get 100 times 1 plus 0.2 plus 0.2 squared. Notice I just did the same thing I did before. I have 102 spots. I can factor it out to the left. Now, you might want to take this one more time to make sure, but as I can see, what I get is that D3 is 100 times 1 plus 0.2 plus 0.2 squared. D2 is 100 times 1 plus 0.2. I see the pattern, probably because I did a million of these. The pattern that I see is that dn is 100 times 1 plus 0.2 plus dot 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 plus 0.2 to the n minus 1. How do I know it's n minus 1 here? Because when n was 3, I ended at 2. When n was 2, I ended at the power of 1. So that's how I realized that I'm just going to keep adding powers of 0.2, and I end at n minus 1. It turns out this is called a geometric sum, a finite geometric series, which we'll be using a little bit later. But this finite geometric series, it's a formula, and this formula was developed by a German mathematician of the name of Gauss, who supposedly, rumor has it, came up with it when he was, I don't know, 5 years old. So he supposedly is a child prodigy. I don't know what his parents were feeding him, but he came up with this formula when he was a child. And supposedly, I don't know if this is true, it's probably an urban legend. So I have this formula here, 1 minus r to the n over 1 minus r. In my case, r is 0.2. So I would substitute that 0.2 in, and I get that dn is 125 times 1 minus 0.2 to the n minus 1. Why do I have an n minus 1 here? Well, that's because my last term ended at n minus 1, not n. So this n over here should really be replaced with n minus 1, because I didn't end with the value n, I ended up with n minus 1. So that's my formula. By the way, where did the 125 come from? Well, 100 divided by the quantity 1 minus 0.2, it turns out to be 125. So that's where that number comes from. I think they actually got it wrong. Actually, yeah, because you see that they have an n here, and I have an n minus 1. I did not make a mistake this time. They have an error. But now that you know what they want here, know that you might could do the work just like I did, but know that they want an n minus 1 up here and not an n here, not an n minus 1. But I am right, and this time I always joke, let's check if Webassign is right. Webassign is not right. So they want to know what quantity of the antibiotic remains in the body in the long run. Well, they want the long-term behavior. Well, it turns out in this formula here that 0.2 to the n minus 1 actually goes to 0 as n gets large. Why? Well, take 0.2 to the 100. We did that in the 1 o'clock class. Somebody did 0.2 to the 100 on their calculator, and they got something like some number times 10 to the minus 70. So as far as we're concerned, that number turns out to be 0. So since it converges to 0, and I can toss 0 in here, and my answer is 125. So the long-term behavior is 125. Now, you didn't have to do it this way. You could also do it the other way on Excel and drag down the data, and you would get the same answer. So that is up to 5 now. And I'm going to stop this so it doesn't turn out to be too long of